Hi everyone. Today I want to talk about linear types. I saw a great talk at the Zurich Haskell meetup, which I of course could attend from my home outside of Philadelphia, um, about linear types by my Twig colleague Utku Demir. And it got me thinking and it got me doing a little experiment, so I'm going to share some of my experiments with you. If you want to follow along from home, there is a link in the description below to a GitHub repo where I post the files that we're going to be looking at today. So the idea here is that we want to use linear types to make sure that a resource is used. So the general idea is going to be sort of around we don't want to be able to duplicate money in this case. Let's sort of we'll just read top down through the file here. So we need a few general linear utilities here. This UR stands for unrestricted, but unrestricted is very long. So we just abbreviate it as UR, and it allows us to embed something. If we want to be able to use many of something, but it's embedded inside of a type that we can only use one of, then we can tuck that in a UR. We'll see an example of this, but it allows us to use something unrestrictedly, even in a linear context. Oh, and I should say, linear types are about being able to use something exactly once in a function. So if we have a function that has a linear argument, that argument must be used exactly once. If it's used not at all, we get an error. If it's used more than once, we get an error. And this allows us to do some cool stuff. So there's a lot of cool stuff. I'm just going to highlight one bit of cool stuff in this video today. So we also need a way of chaining together various linear operations. So here we have the reverse apply operator ampersand, but a linear form of it, where the argument, the x, gets bound linearly here. So this %1 arrow is the linear arrow. So we can only use x once in the body. And the function itself is a linear function, and it also must be used just once. So everything is linear about this. That's why I have to define it here. I can't just import it. But note, I haven't done any other fancy imports. So there is a linear base that Twig is working on, but that's not in play here. We're not doing any fancy imports. So the idea, the sort of central abstraction that we're going to do is now pictured up on the screen. So the key step here is that we have a sense type, and this is going to count the number of cents that we have. So this can be an int because we're always going to have a whole number of cents here. So that's why it's not dollars or something else like that. And the idea is that I have a function with cents that I choose how many cents I'm starting with, and then there's going to be some transformation that takes these cents and produces some result. But I want to make sure that there's no duplication of money in this. So very critically here, I'm going to say that cents are used linearly in this function. Well, if cents are just used linearly, that means they have to get used up. How are they going to get used up? Well, they're going to get spent into a bank. And so I have this other bank type which stores how many cents the bank has. And when I'm all done with my function here, after I've spent all of my cents, I'm going to return some result, can be anything, any type R, as well as the resulting bank. And this is going to be some function that's going to be supplied by this continuation, right? This whole thing is an argument to with cents. And so it's essentially this continuation from the function. So it's going to compute on these cents. Eventually, it's going to have to deposit them all into the bank because there's nowhere else for the cents to go. And then I'm going to return whatever the result R is plus the amount of cents in the bank. Now, linearity is going to ensure that no matter what this function is, the resulting number is going to be the same as the input number. So in a real application, I wouldn't even need to return the resulting number because I always know what it is. But in this, I want to be able to test it. So I'm actually going to return the number of cents that have been spent in this function. And we might imagine, if we didn't have linearity, we could just return the same bank that we got in, which would have 0 cents in it. Or we could take the cents that we get and spend it many times. But linearity is going to ensure that none of that happens. So the body of this function is not really all that interesting. It just takes my continuation function f, and it initializes a bank with 0. It passes all n cents to the continuation function, and then unwraps the result. So fairly basic implementation here. We have a few operations that we can do on these cents. So we can split the cents. So if I can say how many I want to split off. So if I have 50 cents, maybe I want to divide that into two piles of cents. I have a 10 cents and then another 40 cents. And so here I'm going to say, I would say 10. And then this is going to split my cents into two different collections of cents, which can be spent separately. I might want to check how many cents do I have remaining. So I can view the number of cents. So this returns to me the number of cents. But because this is a linear consumption function, right? This takes cents linearly. I have to return the cents back. Otherwise, it looks like they've been consumed. So if I don't return them back, that's very bad, and it means that this view function would actually consume the cents that I couldn't use again. That's not what I want. On the other hand, this int that I return, this needs to be an unrestricted int because I want to be able to use this in comparisons, right? Does the less than function use its result exactly once? I don't know. I don't care. I want an unrestricted int so I don't have to ask such questions. And so that's why this is unrestricted right here. The spend function is actually what uses up the cents. So here, I take a certain number of cents, and then I'm going to deposit them into the bank by transforming this bank. And the bank itself also has to be linear, so I don't end up duplicating the bank or creating a new bank out of thin air and returning that, right? Note that both bank and cents would be exported from this module abstractly. So it's one interesting thing to note here is that if we didn't have the spend function, then there is no way we could ever call with cents because there's no other function that takes cents that doesn't produce cents. And so this is sort of a key point here. Okay, so that's with cents, or that's our little module that deals with money. And here is a main program, and I like to make it main. This isn't just some function, but this is actually a program that I could compile and run. It's easier, more convenient to do this just within GHCI, so I'm not gonna compile it and run it separately. But this is really just a normal main function. This is just normal I/O, as our usual friend. And this just asks for, if I run this, I say how many cents do I start with. Let's say I start with 15 cents. And then it spends it using triangular numbers. I just needed some silly mutator function. The details I'm not going to go through here. But it says it spends 1 cent, and then it spends 2 cents, then it spends 3 cents, and then 4 cents, and then 5 cents, and then it's out. So it takes a total of 5 steps. As we see in the output. If I run this again and I have 16 cents to start with, that actually takes 6 rounds because there's 1 cent left over. The details in here, not important. You can stare at that if you want, but that's just, it's not worth the time in there. Other than this is just some arbitrary function. I could do a lot of different things here. Okay, so all is well and good, but there's an interesting thing that happens in this view function. So I said that I need to return the cents from the view function in order to check how many cents there are. So let's look at that a little bit more closely. So here in my function, I check to see how much money we have so that I can compare it to the amount that I'm about to spend. N tracks the amount that I'm about to spend. And so if I don't have enough, then I want to stop. Right? I don't want to recur and keep spending money. And so that's why I need this view function. If I didn't return the cents out of the view, if I didn't get this money 1 back out, then this money 0 would be consumed and I wouldn't have any more money to spend, right? And this invariant that I want, that the result of with cents is the same as the input, I would lose that. That would be no good. And so this view function really does need to return back this cents object. That's very important. You also might be wondering, why am I using this funny ampersand and reverse apply instead of using normal let? And that's because let doesn't yet have the right inference around linearity. This is something some of my colleagues are working on at Twig. We will get there. For now, we just have to use this ampersand. It's a bit ugly. Bear with us. Still under construction. Okay, so we have this, but this view function, there's something suspicious here. If it's returning cents, how do I know that the cents being returned is the same number of cents that I'm sending in? So there's nothing stopping us from doing that. Maybe my API, it has this nice surface that preserves linearity and looks like it preserves the number of cents, but maybe something nefarious is going on inside. So let's jump over to linear2.hs, which is much the same, but I've done something dastardly in view. So in my view function now, it still has this linear type. I'm now saying n minus 1. You might wonder, well, how is that possible? How could I do n minus 1 if I said that I'm going to use this linearly? Well, actually, if I look at the definition of sense, the int stored inside is unrestricted, right? This arrow here is not a linear arrow. This is an unrestricted arrow, so I can do whatever I want with n inside of my view function, including subtract 1 from it. So now if I compile this, the main is just the same as what we saw before. I can run main, and then now if I start with 15 cents, ooh, I had to look at the number of cents, and every time I look at the number of cents, one of my cents disappears. I'm losing pennies here. This is very bad. And so this violates our notion. Now of course, users would quickly figure this out and not use this library anymore. But I'm a Haskellr, so I want to show this in the types. I don't want to have this type of view that leaves it possible for my library to be taking away my carefully earned cents. This would be bad. So let's go on to linear 3. So in linear 3, I've rejiggered this to avoid this possibility. So this is a bit more complicated than the last one, but it is a way of avoiding that possibility. The idea here is that instead of restricting the way that the cents are used, I'm going to have something I'm calling a token. So we can imagine that the cents are locked in a sort of a wallet. And in order to get any access to it, I have to spend this token. And the token must be used linearly. So that says that I must be, because my token must still be spent linearly, and we'll see this in the code in just a moment. Because I have to spend the token linearly, I still have to use my cents linearly, but it means that the tracking of the linearity is separate from the tracking of the data. That's the key point here, so I'll say it again. The tracking of the linearity is going to be all about these tokens and not about my data, my number of cents. So let's see exactly what that looks like. So again, it's a bit more complicated, and I apologize for the sort of more advanced syntax here, but this would be the way to do it. So now my withCents function, instead of just being linear, note it's actually not linear in the sense. This is a regular old arrow, but instead it is linear in the token. The sense also is now indexed by a phantom parameter t. So we see that my sense is indexed by t, and my token is also indexed by t, and here critically it's the same t. So we'll see in my other functions down here. Let me scroll them into the window. Here we are. So in spend, critically, the t, this index t, must be shared. It must be the same t between the token and the sense. So I can't use my sense anywhere. In fact, all three of these functions that deal with sense all take a token as well. And that's the critical thing, right? Remember, sense is going to be abstract, so I can't get the number out. The only thing I can do is call one of these functions. This is my API. All of these functions require a token. All of these functions use that token linearly. So I can't do anything with sense without my token. But the upshot is that my view function, it has to produce a new token because that's the thing that tracks linearity. That's the thing that got consumed, that I have to be careful about it getting consumed. But it doesn't return new sense. My sense stays the same. It's just passed in. And because I'm working in this beautiful, pure functional programming language, then I don't have to worry about sense being changed. Right? I know sense can't be changed by viewing it. There's no way I could do that dastardly -1. So let's look at this a little bit more depth. So here in withCents, I have to create essentially a new phantom parameter t, and I can conveniently doing that using essentially the st trick. Some people might know about the st trick of using this higher rank type. And so it's saying that the function that I supply must work for any t. So I can't make any assumptions about what t in particular. So I can't relate this to anything that's happened outside of this continuation function. Again, the implementation is kind of boring. Split has to be rewritten a bit annoyingly because, again, I need to pass in these new tokens. And Haskell doesn't have a way of doing existentials yet, right? So I can't sort of return T1 and T2 from split the way I might want to. So instead of that, and by the way, if you don't understand the existentials comment, don't worry. Maybe another post. Definitely another post, but it might be sometime. So here, I'm going to create two fresh T1 and T2 because my new sense are going to be associated with T1 and T2, and I'm going to have tokens associated with T1 and T2 to work with them. So it's a little bit annoying that I have to do it this way, but it still works quite well. And then my spend, again, that takes the token and the cents, and then it increments the bank. If we look at the program, this is quite similar to what we had before. I still set up a with cents in this nice way, but now I have this token. And so every time I want to access my money, I have to use the token. So here I pass toke 0, and I get back toke 1. But toke 1 is going to have this same index, that same t. Let's just scroll back up and see that for a sec. Here, the token I get back, this is the same t. I'm not using another for all to generate a new t, because I want this to be able to be used with the same cents. And so here I get this toke 1, and then I can use toke 1 in spend, or in go, no, I guess not in go, in split, with the same money. I don't have money 0 and money 1 as I had in previous versions. And so there we have it. Now this version still compiles. I get some warnings because I have a debug compiler here, but that's fine. And then if I run this, now indeed I'm not going to lose any cents as I'm computing, because I can't. My types prevent it. Anyway, I hope that was interesting. Thanks very much for watching.